In this session, I will talk about the sequences. A sequence is said to be convergent if it approaches some limit. That means formally, we can say that the sequence A sub n converges to the limit S if the limit at infinity of A sub n equals to S. But we will check a few sequences and check their convergence or divergence. We may also notice that every bounded monotonic sequence converges, every unbounded sequence diverges. That's another tool that we can use in order to determine convergence. Example number 1. Determine whether the following sequence converges or diverges. If the sequence converges, find the limit. That means one more quick note. For the sequences, we only looking for the limit. And if the limit exists as a finite number, then the sequence is convergent to that number. Please remember, because in order to check convergence or divergence of the series, we're using tests, lots of tests. We're not applying any test for the sequence, just simply the laws of limit. Okay, that's we do have a sequence 2n plus sine of n over n plus sine square of n. For this one, we may use, in order to compute a limit, we may use a squeeze theorem. And I will compute a limit of 2n plus sine of n plus sine square of n. Some of you probably see right away that function sine of n, sine square of n, they have little values. The maximum value is 1. That means they theoretically do not exist at infinity. That means the only leading functions are 2n and n. The ratio of the leading coefficient is 2. That means the limit is 2. The sequence converges to 2. But let's actually, as I said, let's apply the squeeze theorem. And I can write I can write my entire sequence 2n plus sine of n plus sine square of n. And I can squeeze between two functions. I will copy 2n, and the maximum value of sine of n is 1, and maximum value of sine square of n is also 1. Then I will try to get a function less than my original formula. That means the minimum value of sine of n is -1. And since the sine is squared in the denominator, the minimum value is 0 because all of the squared values are positive. That means plus 0, I can write it down. And now as n goes to the infinity, we can nicely see that this limit is 2 as n goes to the infinity, and also this limit is 2 as n goes to the infinity. That means by the squeeze theorem, the middle formula is forced to have the same limit, 2. That means that's what we just said. The sequence is convergent to 2. Sequence number 2. Square root of 4n minus 1 over n plus 1. In order to find convergence, we have to compute a limit. Square root of 4n minus 1 over n plus 1. We can just compute a limit of the inside quantity and then apply the outer function, square root. Since the function is like continuous function, if we will think about the x, that means the limit inside is the ratio of the leading coefficients. 4n over n is 4, square root of 4, 2. The sequence converges to 2. Another one, 3e to the n plus natural log of n over e to the n. Again, limit at infinity, will give me the behavior of this sequence. And we can see that we can compare the growing rates, the relative growing rates. The fastest function is e to the n in this case, and we have e to the n and e to the n. This is coefficient 3, this is coefficient 1. The ratio of the leading coefficient is 3. The sequence converges to 3. Another one, 1 plus negative 1 to the n over root n. So we can use probably the squeeze theorem right away, or the same like the first example, we can think that the values on the top will be sometimes 2, sometimes 0, because negative 1 to the n could be 1, 1 plus 1 is 2, or negative 1 to the n could be negative 1, 1 minus 1 is 0, that means 2, 0. But in the denominator, we have a big number, square root of n, square root of huge numbers at infinity. That means 2 over huge number is 0, small number, or even 0 over huge number is also 0. Okay? That means I can possibly rewrite, if n is 1, this will be 0. If n is 2, negative 1 to the 2 will be positive 1. 1 plus 1, 2. Actually, this is n. And then again, 0 over root n, 2 over root n. But we can nicely see that these terms, of course, are zeros, but these terms are, if n is 1, I really have to put the values. I did focus on the numerator only, and so on. But we can see 0 and 2 over square root of 2, 0, 2 over square root of 4, 0, and then 2 over square root of 6. But every other terms definitely are getting smaller and smaller. They approaching, at infinity, they approaching 0. 1 plus negative 1 to the n will be 0. That is convergent to 0. But let's try to work it out. The maximum value is 1, that means this will be always 2 and everything gets less, or value is negative 1, 1 minus negative 1, 0. That means this goes to 0 definitely, as n goes to the infinity, and 2 over huge number is also 0 at infinity. That means the middle part, which is our sequence, is forced to be 0 by the squeeze theorem, convergent to 0. Another one, e to the power of 1 over n over arctan n. And that means let's check a limit at infinity of e to the power of 1 over n. And I can just rewrite for you as the inverse tangent of n. That's arctan of n. Okay, 1 over n is a big number. I mean, 1 over big number, 1 over n, as n is infinity, is 0. And inverse tangent at infinity is pi over 2. That we do have e to the power of 0 is 1 over pi over 2. It's just 2 over pi. Finite number. The sequence converges to 2 over pi. And just recall, I can draw a function inverse tangent of x. And my drawing is and we have invisible line, horizontal asymptote at pi over 2 and negative pi over 2. And just to know the behavior. That's the reason that I put pi over 2. Another sequence, nth root of 7. Let's find the behavior at infinity. Nth root of 7. I can rewrite this as a 7 to the power of 1 over n. 1 over big number is small, 0. 7 to the power of 0 is 1. The sequence converges to 1. Natural log of n over logarithmic function based 7 of n. Let's find the limit. Limit at infinity of natural log of n over log base 7 of n. I have two different ways to compute this limit. I can apply the L'Hopital rule, or I can change the base for the logarithmic function in the denominator. Let's change the base. I will keep my natural log of n, and logarithmic base 7 of n I can rewrite as a ln of n, ln of 7. And let's simplify. I do have natural log of n, and dividing by fraction means multiplying by the reciprocal. Ln of 7, ln of n. And we can nicely see that the final answer is just ln of 7. Actually, I can natural log of 7. The sequence converges to ln of 7. Another one, ln of quantity 2n plus 1 ln at infinity behaves like infinity, but let me write everything. Limit as n goes to the infinity, ln 2n plus 1 minus ln of n. As we can see, we do have infinity minus infinity. This is indeterminate form, but we can definitely nicely deal with this because the difference of two the same logarithm I can rewrite as one single logarithm, just simply dividing the arguments. And now computing a limit of the inside, I can see that the limit at infinity of the quantity inside is 2. The final answer is ln of 2. Yeah, I just apply this limit. That means this sequence is convergent to ln of 2. Okay, another one. A little bit of exponential form. 9 to the power of n over 3 to the power of 2n minus 1. Let's check the limit at infinity. 9 to the power of n, and then we have 3 to the power of 2n times 3 to the power of negative 1. Because when we have multiplication, we adding together. Of course, adding a negative number is subtraction. Let's simplify first. Because looking at first, actually, we have 9 to the n, that's exponential function at infinity is infinity. And 3 to the 2n or n is also infinity. That we do have a form infinity over infinity. But we may apply the L'Hopital rule, or we can simply simplify first. 9 to the n, and then 3 to the power of 2 is 9 and n, and 1 to the negative, 3 to the negative 1 is 1/3. And we can nicely see we do have the same exponential function, which we can cancel out, and 1 over 1/3 is 3. That means this sequence is convergent to 3. Converges to 3. Okay, another one. Let's check the limit at infinity of, I can write 4 to the n, and 3 to the power of 2 is 9 to the n. Okay, and we do have 9. I mean, either way, it's a good form. Looking at 9 to the n over 4 to the n, we can definitely see that function 9 to the n grows much, much faster that means infinity. Or if we have this form, if the number taken to the power of n is greater than 1, always the value expands to the infinity. That means this is infinity, which means the sequence diverges. Okay? 3 minus pi to the power of n. Let's check a limit at infinity. 3 minus pi to the power of n. That means the same thing. If I will know that this number for the exponential form, exponential function, if the base is greater than 1, then its values approach infinity. If the number is less than 1, then it goes to 0. And let's investigate the quantity 3 minus pi. Pi is like 3.14. Okay, that's when we can see this number. It's actually, let's say, -1. And we do have -1, that's when we have the alternating part. We have -1 to the end, and we have 0.14 to the end. But 0.14 to the end, the number is less than 1. That means this definitely goes to 0. This form is telling me that it's alternating. That means positive, negative, but the terms are getting smaller and smaller. That means the limit is 0. However, we may apply the theorem that's taking absolute value. Okay, taking absolute value, we actually getting a limit of only 0.14 to the power of n. Since -1 to the n becomes 1, that means this limit is 0. If the absolute value is 0, then the original one is also 0. I can actually remove, but this is the blue part is the absolute value. That means the series is the sequence is convergent to 0. Convergent to 0. Okay. The sequence n times sine of 1 over n. Let's see how this behaves at infinity. N sine of 1 over n. That means this is infinity. 1 over infinity, 1 over big number is 0. Sine at 0 is 0. That means theoretically we do have indeterminate form. That means let's try first of all to rewrite. I will keep sine of 1 over n, and instead of multiplying by n, I will divide by 1 over n. And I nicely see that I can apply the L'Hopital rule, but also I can name 1 over n, I can name t, okay? And we can see that t, let me write, 1 over n is t, but as n goes to the infinity, this goes to 0. Okay, t goes to 0. That means I can rewrite my limit as a sine of t over t, but t goes to 0. And we remember this property, sine of 0 over 0, t over t as t is 0 is 1. That we can even skip the L'Hopital rule just using the property. This sequence converges to 1. Converges to 1. Okay. N plus 3 factorial over n cubed times n factorial. In order to compute this limit, we have to simplify the factorials. That means, remember, I will keep n cubed. And now we do have n factorial and n plus 3. And the number n is less than n plus 3. That means I will keep n factorial. And the quantity n plus 3 factorial, I can rewrite as n factorial times n plus 1 times n plus 2 times n plus 3. It's the same like let's say 10 factorial over 7 factorial. 7 is less, and 10 factorial I can rewrite as a 3 number less, which is 7 factorial, like this one, and then times 8, times 9, times 10. One number more, another number more, and then end up at 10. And of course, we can cancel out. That means that's the point. I can cancel out this. And now I see that my limit at infinity is just the ratio of n cubed. And if I distribute everything, I also have n cubed as a leading function. Both of them has coefficient 1, it's 1. Converges to 1. 1 plus 1 over n to the power of n. We probably recognize this limit from different sections in our calculus textbook. And we know that this limit is actually e. Converges to the quantity e. But let me, and I will really like you to remember this, 1 plus 1 over n to the power of n at infinity is e. But I will solve for you this one just to prove. I will use the L'Hopital rule. That's the limit. And let's rewrite n is x instead of n. As x goes to the infinity, 1 over x to the power of x. This is the form 1 to the infinity. And in order to apply the L'Hopital rule, I have to really rewrite this. That means, first of all, I will rewrite this power form as an exponential form, e to the power of ln, and I will copy this quantity. We know that e and ln are the inverse to each other, that means they kind of cancel out. Okay. Now, the x in the exponent can travel in front of the ln. And the only thing is now I have to focus on my exponent. That means the final answer will be e to the power of this number. That means let's solve the limit of infinity only on that exponent, x ln of 1 plus 1 over x. Okay. Let's rewrite this limit. Because what we do have this 1 over big number is tiny, smaller, 0. ln of 1 is also 0. But we do have 0 times infinity. We have the indeterminate form, product form. In order to apply the L'Hopital rule, I need a quotient, 0 over 0 or infinity over infinity. That means I will rewrite this as a quotient. ln of 1 plus 1 over x will stay on the top. And multiplying by x, I will switch for dividing by 1 over x. And now I have 0 over 0. I am good to apply the L'Hopital rule. Limit as x goes to the infinity. And derivative. Derivative of ln of quantity 1 plus 1 over x will be 1 over that quantity times derivative of this quantity. Derivative of 1 is 0, derivative of 1 over x is negative 1 over x squared. And derivative of the denominator is the same, negative 1 over x squared. We can cancel out. Sub 1 over big number is 0, and 1 stays, the limit is 1. But of course, this is that one. Yeah, that's the one. That means the final answer of the original one, it's actually e to the power of 1, it's e. That means I did prove that limit. But as I mentioned, this is one of the really special limits. We don't have to really go through the whole process. Please just remember this limit. And now let's look what I have on the other side. I have additional coefficients, 7, 1 plus 1 over n to the power of 7. And if we will get back to this slide, and if I will place 7, I can use maybe different products. 7, 7, 7, 7, And I can actually keep that 7. We see 7. Of course, the answer will be 7. That means e to the power of 7. And the same I can play. I'm trying to remove that 7 because that wasn't the part of my. Okay, good. And you can equal some. That means what I can tell you, of course, it's also easy to prove this, but the limit at infinity of the quantity 1 plus a over n and b times n, that's b. That means this is still e, but the coefficients a and b will be just the answer of the previous image. That means will be the final answer will be e to the power of ab. That we can see right away that this sequence converges to e to the power of 7. Which I can just confirm that limit at infinity of that form is e to the power of 7. Okay? But also this extra limit. Oh, and we can nicely see that this converges to e, and now we can see we do have 2, and we have negative 2, negative 4, because it's extra, different sign, different value. That means this should be addition. Right? I can now write this limit as n goes to the infinity 1 plus negative 2 over n 2. That means negative 2 times 2. Okay, another sequence. Negative 1 to the n, and then 3n plus 1 over 7n plus 5. So let's find the limit. And this sequence includes the negative 1 to the n, that means the alternating one. And what we can do, we can try to find a limit of absolute value. And we remember, if the absolute value equals to 0, then the original sequence is also 0. If the absolute value of this type of sequence is not 0, then the original sequence is divergent. This means the absolute value looks like 3n plus 1 over 7n plus 5 without this negative 1 to the n, because it becomes positive. And we can see this limit is 3 over 7 different than 0. That we may think it's not 0, but we may also think that this sequence behaves at infinity like positive 3 over 7, negative 3 over 7, positive 3 over 7, negative 3 over 7. It's alternating between these two numbers. That means it's not going to one direction. Diverges. This sequence diverges. Okay, the same situation. If we take absolute value of this sequence, negative 1 to the n, e to the n squared plus 3 over n squared plus 1. Taking absolute value, we're losing the alternating part. However, the limit is not 0. E as a coefficient of n squared and just 1n squared. The leading functions are n squared. The ratio of the leading coefficient is different than 0, e. That means the sequence behaves like positive, negative. I can kind of say positive, negative, e. Of course, it's really informal. We have to just think this way. This means that the sequence doesn't go in one direction, doesn't approach one finite number. Divergent or divergent. And another one, and I believe this is my last one, the same thing. If we will take absolute value, I believe we can see the number different than 0. N plus 3 over 9n squared plus 1. And that's the sequence. Taking absolute value, I'm only getting the positive part without the alternating. N plus 3, 9n squared plus 1. We may think that it's 0 because it's n squared, but we still have the square root. That means the leading function is n, and 9n squared if we will factor out and simplify. That means the limit is n over 3n. We can nicely simplify n squared of the square root as a n because n is positive. And that means this is just 3n. The answer is 1/3, which is not 0 because we took the absolute value. That means again, positive 1/3, negative 1/3, positive 1/3, negative 1/3. The sequence is divergent. Diverges. Thank you.